Okay, so shall we start? Good to know that most people are still around. So, anyway, my aim would be to describe and prove Schoenberg's theorem, which characterizes the positive definite kernels on the sphere. Okay, so there is also a general theorem due to Bochner, which is what I will start with. But maybe at some point of the proof, I'll sort of explain only the sphere case. Bochner's result is also not very difficult to prove, but I'll avoid some technicalities. Okay, so before we get on to Schoenberg's theorem, so let's recall the classical theorem of Bochner. So if you have a positive definite function, so I'll assume continuity, but positive definite. So maybe I should include a definition is positive definite if, so one way of defining this is you take endpoints from the real line and look at the matrix xi minus xj. So this is the n cross n matrix is positive semi-definite, okay, PSD. So you can also replace this with a integral condition. So f of x, f of y bar phi of x minus y dx dy. So this is positive for every f in L1 or continuous functions with compact support or any of that will do. So these two are equivalent definitions. It simply says that phi is a positive linear functional on L1. Okay, that is the. So the theorem says that any such function is a Fourier transform of a positive finite measure on the real line. Okay, so phi is positive definite. We'll keep using PD. So phi is positive definite if and only if phi equal to mu hat. So this is the Fourier transform of mu for some positive finite measure mu, okay, on R. So that is on the real line. Of course, it has been extended to all locally compact abelian groups. So this is also true for locally compact abelian groups, right? So for such a group, the dual is also a locally compact abelian group, and you look at positive finite measures, look at the Fourier transform of them, you will get positive definite function. So one has to define what is meant by positivity. So you can use either this definition or this definition. In this definition, you look at, you take points and look at the corresponding matrix defined by point 6. So in particular for S1, so if I take the circle group, right? If I take a positive definite function defined on S1, then it's given by the Fourier transform of a positive finite measure on the dual. So dual of S1 is just integers. So positive finite measure on that dual is simply a bunch of positive numbers, right, which is summable, right? So one will get that n e to the I n. Okay, so an's are positive and summation an is finite, right? So that is the finite part of the measure. An's are positive tells me it's a positive finite measure on the dual. You look at the Fourier transform of that, you will get your positive definite functions. So our aim is to prove something similar for the for spheres on Rn. So one should have something like the dual, which is going to be a certain set of integers, and you will have positive measures there, and you take the Fourier transform. Well, the Fourier transform, what you do is you view the sphere as a homogeneous space, and there is a way to sort of, you can think of how you will do this for compact groups, right? If I give you a bunch of numbers, you can construct the inverse Fourier transform using the representations of the group, right? So you will do something like that, but we will be looking at what is known as G-invariant kernel. So that will essentially say there is certain kind of invariance. So you will not be looking at all the representations like this, only certain class 1 representations, and that will give us the result we want. Okay, so I'll start with some generalities and then write down the assumptions on the space we are looking at first. Okay, so so this is, think of this as just a motivation for whatever we are going to prove. So let X be a space, so some set be a space. So we define positive definiteness in general first, and then we will look at G-invariant ones. Yeah.
Can you just make a quick comment?
Yeah.
Say that it's function the real value, then maybe this already gives you on S1, it gives you check what you get cosine.
Correct. Correct. Yeah, all right. So what Abhinav is saying is, if we assume that these are real valued, then instead of e to the inx, you will have the cosine functions, which are the Chebyshev polynomials, which are special cases of Jacobi polynomials, okay, or Gegenper polynomials. So the general result for the sphere is going to be that it is going to be a linear combination of Gegenper polynomials or Jacobi polynomials more generally. Well, I keep saying more generally because the sphere, instead of the sphere, one can look at rank 1 compact symmetric spaces and you have similar result. Okay. Okay, so let's set up the general general notation. So X be any space, we want to define positive definite kernels on X. Okay, so you have a kernel which is defined on X cross X to, so well, I'll keep writing complex valued functions. So this is just for the definition, is called positive definite, or is said to be positive definite. It's said to be positive definite. So we'll simply write PD from now onwards. If so, the same definition, except that we don't have the group structure on X, so we simply take the points. Okay, so you take points in X and then look at the corresponding matrix defined by. So this is an n cross n matrix. This is positive semi-definite. Okay. Right. I'll come to why here we look at xi minus xj, because of that's just simply the G invariance. Right now there is no group here. Right. This is simply a set. So we'll assume that if X comes with a topology, so X is going to be the sphere in Rn or a G space, so where a group acts, so it will come with a topology. So if X comes with a topology, we'll assume K is continuous. So if X comes with a topology, we'll assume that K is continuous. Okay, so let's set up the assumptions on X. Assumptions on the space X. Okay, so X is going to be as nice as you want. So this is going to be a compact 2-point homogeneous G space. So G is going to be a compact group. So G acts on X and X is a 2. So what does that mean? That means, so we have So there is a G action on X as nice as you want. So you can assume X to be a Riemannian manifold and G acts like diffeomorphisms and whatnot, all that you want. Well, in our case, it's G is just SON and X is the sphere, so as nice as possible. Okay, so X is a metric space with distance functions denoted by D, distance function D. D is, so that this is the 2-point homogeneous part. D is strongly invariant under G action. Okay. Under G action, what does that mean? That means if I take x1, x2, y1, y2 in the space X, so pair of points at same distance, so d of x1, y1 equal to d of x2, y2, then we have a, well, this happens if and only if there exists a G in G. So G acts on X. So G will take x1 to x2 and y1 to y2. So Gx1 equal to x2, Gy1 equal to y2. So as close as doubly transitive as it can be. Okay, was there anything else? Yeah, okay, so I think this is enough. So, well, in such a case, it's known that if G is an infinite group, then a connected group, then it's a rank 1 compact symmetric space. Okay, there are cases where X is finite, and you have a finite group acting on it, which are also important from the problems we are discussing, but I'll not get into those spaces at all. Okay, so well, so let's realize X as a quotient of G. So you fix a point x0 in X and look at the stabilizer of x0. So let's call that H. So you look at all those points in G such that G fixes x0. So G dot, well, G dot x1, G dot y1, etc. are the action of G on the space X, right? So you look at all those elements in G which fixes a fixed point x0, and this will be subgroup of H and it's compact. Okay, so it's a compact subgroup of H, and then as usual you can identify X as a quotient of G, right? Homogeneous space. So in particular, since these are all compacts and so on, X will have a G invariant measure. So in particular, X carries a G invariant. Okay. Well, you can, so let's call that mu, and we normalize mu such that the total measure is 1, right? It's a compact space, so we can do that. Okay, so the example we want to keep in mind, so this is the general setup. So the example we want to keep in mind is X is the sphere Sn-1 in Rn, the group is SON, and if I choose the point x0 to be, well, the subgroup which fixes any point is going to be conjugate to SON-1, but at times we'll choose a point on the sphere which is the north pole or whatever, the first basis vector or the last basis vector, and then we can identify the space Sn-1, the sphere, to be a quotient of SON with SON-1. Okay, so that's the space we will look at, and on the sphere we have the rotation invariant measure, which is the measure mu. Okay. So in such conditions, so one should also notice that whenever we have a situation like this, the functions on X can be thought of as functions on G, which are right invariant, and there is also a left action of G on X, right? So we will be looking at functions which are H invariant under that action, and they would be identified with H bi-invariant functions on G. Okay, so I'll keep saying this whenever it is necessary. Okay, so what is our aim? Aim is to characterize the positive definite kernels K which are G invariant. Okay, so what does that mean? That means K of x comma y is equal to K of gx gy for every G in G. Okay, so that is the invariance, G invariance of the kernel. So let me comment on the expression here. So whenever you have a G, if your capital X, the space X itself is the group, the G invariance is what brings you to this kind of expression. So okay, so let me tell you what that means first. Okay, or some remarks, and then let's see. The space of positive definite kernels so is closed under multiplication and positive linear combination. So that is one observation. So that's easy to see. The space of positive definite kernels on X is closed under multiplication, so pointwise multiplication and positive linear combinations. So that's follows immediately from the properties of positive definite matrices. So if I take two kernels K1 and K2, I can multiply them, I'll get another positive definite kernel, because if you look at these matrices, that is the Schur product, right? Entry-wise product is the Schur product, and Schur product of two positive definite matrices is again positive definite. And of course, if you take linear combinations of positive definite matrices with positive coefficients, then you will get a positive definite matrix. Okay, so those two are sort of, and when you take combinations, you can actually take infinite combinations as long as it converges nicely. Even then, you will still get a positive definite kernel. Okay, so that is one. The positive definite condition. So when X is nice enough, where there is a measure, blah blah blah, instead of looking at just the matrix, if X comes with a measure and so on, you can change this to an integral condition as we have done for the real line. So you can, so the positive definite condition can also be written as, so you can replace the summation, so that's like a Riemann sum which approximates the integrals. So you will get something like this: kxy phi x phi bar of y d mu x d mu y and so on. Okay, greater than or equal to 0. So appropriate measures and so on, you can always approximate the integral with the summation and vice versa. So well, in the case we are looking at, it's a sphere, so you can replace the discrete condition like this with an integral condition like this. Okay, so if X itself is a group, which is the first case we wrote down, and if I have G invariant, okay, then if it is G invariant, you can think of it as a function on the group itself instead of G cross G. Well, how do you do this? You can write down K of xy as some function psi at the point y inverse x. So the y inverse x is what you saw earlier. So xi minus xj. So this is because, well, what you do, you define kxe to be I of x, and then this will follow. Okay. So the G invariant kernels on G cross G are functions on G. You can identify them as functions on G. Okay, so well, so if you look at this, K of y inverse x E equal to psi of y inverse x, and of course this is G invariant, so you can multiply by y and you will get xy. Okay, so these two are same. Okay, so that explains the first statement, Bochner's theorem, in terms of why we wrote down in terms of y inverse x and so on. Okay. Okay, so any questions? So in the case of the group, that's what happens, right? So we multiply two things, so that is the Fourier transform of the convolution of those measures. Yeah. So when, well, the case we are interested in is the sphere. So the group G invariance here would mean that kxy is k of gx gy for every g in the orthogonal group SON. Because of this, so this implies there exists a function psi from, because it becomes a function of x dot y, right? It's invariant under SON, so it becomes a function of x dot y. So you can write there exists a function psi such that psi of x dot y is k of xy. Okay. And psi is of course going to be from -1 to 1, 2. Okay, so it's the function of one variable. You can also think of, so one point I want to make here is you can think of this as a, you can view psi as a h, so h remember is SO n minus 1 in this case, by invariant function on G. Okay, something which I'll keep using. Well, strictly speaking, one should write psi of cos theta because of x dot y being cos theta and so on. But what I want to say here is, so we have G, which is SON, and we have the quotient space, so n minus 1. So this is H, right? And if you look at, so write H invariant functions on G are functions on X. And if I further look at H invariant functions on H, so how does it look? So X is the sphere, and if you identify SON minus 1 as the one fixes the basis vector, then SON minus 1 will act on these circles, and if the function is invariant on this, then they are constant on these circles, which means a function on minus 1 1. So functions on minus 1 1 can be thought of as SON minus 1 bi-invariant functions on SON, okay, on G. Okay, so now we can get into representation theory. So we'll need only some representations of SON. Okay. So, well, I'll continue with the generalities. So G acts on L2 of x. Remember x is g by h. Yeah. Sorry? Yes. So also recall that x carries a measure mu, right, which is G invariant. G invariant. And well, we have normalized it so that total measure is 1. So on L2 of G by H, G will act, of course. So if I take a function f, capital F in L2 of x, then small an element from capital G will act on f by usual formula. So this is just f of G inverse x, and this gives a unitary representation because the measure on x is G invariant. So translating by G doesn't change anything. Okay, so that gives me a unitary representation, and it decomposes. Since we have compact groups and so on, it will decompose into irreducible pieces. So L2 of x will decompose into irreducible representations of capital G. So we have two spaces, so let me write both spaces. So I have L2 of x, which is identified as L2 of G by h, right? So functions on x are, so L2 functions on x are L2 functions on G, which are right h invariant, okay? And we also have L2 of G, and that decomposes according to the Peter-Weyl theorem, right? So, well, now onwards the notation will be slightly important because I have to write down all the matrix entries. So, please keep track of I, J, K and whatnot. Okay. So, well, this decomposes. So, this I will write as summation, let's say Vk. So, the K is on the top will denote the representation. Okay. I and J will be the indices which are at the bottom. K equal to 0 to infinity. The whole space L2G also decomposes according to Peter-Weyl theorem. So you will have several copies of the same representation. So this is simply, so let's see, summation m equal to 0 to infinity. This will disappear soon, okay, because our space we are interested in is x. I equal to 1 to dm. So that's a dimension of the mth representation. Vm I. Okay, so maybe I should. Okay, Vm I. Okay, so this notation is slightly different from that, but we will not be using this at all. Okay. So some of this can be. So these are same representations, right? Dm many copies of same representations. Many copies of, let's say, mth representation, and then you add on, right? So that's what L2G is. Now, because of all the identification we have, this is actually a closed subspace of L2 of G. So these representations are some of the representations here, okay, not all of them. The only ones which will appear here are what are known as the class 1 representations with respect to H, which means that they should have a H fixed vector because the functions here are right H invariant. So they will, if you look at the Fourier transform of that, they will, so maybe I can write down that. So if I take a f in L1 or L2 of G by H, and how do you define the Fourier transform? So you look at phi of f, which is capital F G pi G dg, right, as a matrix or an operator valued function, and this survives only if pi has a H fixed vector. Well, that, why is that? That is sort of easy to see. F is right H invariant, so I can put an H here, nothing changes. Because the Hermesher is invariant, that H goes to the other side, so this goes here as H inverse. So, well, maybe I'll start with an H inverse here and bring it to this side as H. but this is a representation, so this is pi g times pi h, and the left hand side has nothing to do with h, so I can integrate over h. So this is simply the first integral, and I integrate over h pi h dh. And you will get, so this is the projection to h fixed vectors. Okay, so projection to h fixed vectors. So if there are no h fixed vectors, that projection is 0. Okay, so the integral itself is 0, which means the Fourier transform of f at that representation is 0. So only those representations with h fixed vectors will survive here. Okay. And well, from general theory one knows that the h fixed vectors are of dimension 1. Okay, so that is because G H is a Gelfand pair. Okay, h bi-invariant functions on G form a commutative algebra under convolution. Okay, so wherever G acts irreducibly, CG also acts irreducibly, and h bi-invariant functions will act irreducibly on h fixed vectors, but h bi-invariant functions are a commutative algebra, and if that acts irreducibly, that space has to be dimension 1. Okay, so this is a sort of a quick proof. You have to believe me. Okay, so anyway, so general nonsense tells you that the h fixed vectors are of one. If it exists, it is of one dimension. Okay, that is something we will use crucially later. Okay, so out of this decomposition, this is the Peter-Weyl decomposition, there are some representations which are class 1 with respect to h, and only those things will come there. Okay, so these are class 1 with respect to h, so which means that h fixed vectors exists. Okay, non-zero h fixed vector as it is, but then from general theory we know that the dimension of that has to be 1. And of course, in this, since this space is compact, the constant functions are there. So V0 will denote, V0 denotes the space of constant functions. Constant functions, of course, it has to be one dimensional because of what I just, right? Because the constant functions are h fixed vectors. So in that particular piece, there can be only one such. In each of them, there would be one unique guy which is h fixed. Okay. Yeah.
You also showed that there one
Okay. So I didn't say that. So these are pairwise inequivalent representations in the sense that this decomposes to a multiplicity free decompose. So I didn't prove that. Yeah. So let's look at the example we have in mind. So I have SON, H is SON minus 1, and I have the quotient space. Okay. So L2 of x is simply L2 of Sn minus 1, which is the familiar space, and we know that it decomposes into spherical harmonic. So let me write it down. L2 of Sn minus 1 is direct sum of, let's say, script m equal to 0 to infinity. So what are hm? Hm are, so this is the space of spherical harmonics of degree m, and well, what else do I know? H0 will be the constants, of course, 0 constants, and I have dimension of HM as well, which is, well, I'll just write down, we are not going to use this. Okay, M minus 2, sorry. Yeah, anyway, that's some expression, we don't need it. So L2 of the sphere decomposes into direct sum of finite dimensional spaces. Each space is defined by the spherical harmonics of homogeneous degree m, and all of them put together gives you L2 of Sn minus 1. Okay. So I made a jump in the sense that general theory tells you it decomposes into multiplicity free pieces, and I'm claiming that this is exactly that. Okay, so I should tell you that these pieces actually correspond to those pieces there. Okay, well, they do. Again, I won't prove this, but I don't know any easy way of doing this. One would be to look at the Laplacian. So the sphere has a Laplacian, and that is the spectral decomposition of the Laplacian. Well, G by H has a Laplacian, and G by H, the Laplacian on G by H is the spherical Laplacian, and this will have to be the spectral decomposition of the Laplacian, because Laplacian is in the center of everything, so it acts like scalar on irreducible components. So each of them will have to be eigenspaces of the Laplacian, and so they have to coincide. Okay, so anyway, it's okay, yeah. So spherical harmonics are okay. So how do I say this? You look at harmonic polynomials, homogeneous harmonic polynomials of degree m, and then restrict them to spheres. Okay, so this would be restriction of homogeneous harmonic polynomials of degree m to the sphere to Sn minus 1. Oh, okay. By harmonic, so what is harmonic? Harmonic means it is scaled by the Laplacian on Rn. Okay, so P of x is a polynomial. Harmonic polynomial means delta of P equal to 0. So delta is the Euclidean Laplacian. Okay, so we have the decomposition. Okay, we are still some time away from the theorem. Okay, so now I need to write down matrix entries. So I'll be somewhat careful and slow with the notation and so on. So let's keep this in mind. We have L2 of x to be as a decomposition of irreducible inequivalent pieces, inequivalent representations of G. Okay, so L2 of x is summation Vk k equal to 0 to. So these are inequivalent irreducible unitary representations of G. Okay, which are class 1. With respect to H. Okay, so that is where we are. So let's give another notation. So this dimension of Vk, let's call that dk. So I'm going to take some basis for this. So let E I K, so remember the K on the top is always the representation. So this is going to be a basis for that particular representation for Vk. Okay, I equal to 1, 2, etc. up to dk. Okay, so this is a orthonormal basis for the space Vk. Well, so these are class 1 representations. So there is a unique vector which is fixed by h. Okay, so that is the first basis vector. Okay, with the first one E1k being the h fixed vector. Okay, so whenever I say unique, I mean up to a constant. Okay, so there is a one-dimensional space which is fixed by h. That is unique. So I choose one from that. Okay, so orthonormal basis. So norm 1. So on Vk we have a representation of G which will be denoted by rho k. Okay, rho k, the representation of G on realized on Vk. So I'm going to write down the matrix of rho k with respect to this basis. Okay, so these are all finite dimensional spaces. So what do? I apply the matrix, I apply the linear operator on one basis vector, expand it, I'll get the basis, I'll get the matrix representation, right? So, so that's where all the ij k will come. Okay, G. So this is an operator from Vk to Vk. I want to write down its matrix representation. So I want to get the ijth element, right? So I apply ej, the jth basis vector, and look at the ith, take the inner product with ith, right? So I look at ejk, right? So that gives me the jth column. So if I expand it, I'm going to get jth column, right? So let me expand it. So this is summation I equal to 1 to dk. So standard way of writing the matrix entries, rho ij. So that is the ijth element of the matrix of rho k with respect to the basis we have started with. Okay, eik. All right. So in other words, what we are saying is the linear operator rho k has this matrix representation, right? Rho ij k, right? This is a dk cross dk. Dk is the dimension matrix, where these matrix entries are given by rho ij k is, you look at this vector, that is the jth column, and you take inner product with the ith basis vector, right? So that is your ijth element. So that's purely linear algebra there. But one has to keep track of the I and j and not. Okay. So, well, why am I writing down all the matrix entries? Because that's where all this positive definiteness properties are hidden. So one of the things you would have learned from basic representation theory is that if I have a matrix entry, a diagonal matrix entry of a unitary representation, that's a positive definite function. Okay. So the statement for Schoenberg's theorem would be that any k bi-invariant positive definite function on G is the sum of k spherical functions. Okay. Sorry, not k, h. Okay. So yeah, I'm used to saying gk, g by k, and so on. So, okay, so let's put together all these functions. So recall that the E1, the first one in the basis collection is the h fixed vector. So if I have one here, that is J1 meaning the first column, right? They are all h fixed, right? If I put an h here, that doesn't do anything to the. So the first column is a class of functions which are h fixed. Okay. So for each of these representations, you look at those first columns. That is what will give you L2 of G by H. Okay. So that's. So let me. Okay. So the functions. So these are functions on G by K. So let me write rho 1 1 K G. Well, this is rho K G, so this is one entry, right? So you look at first basis vector, so that gives me first column. Take the inner product with the first basis vector, you will get the 1 entry. Okay. Well, this is the special guy here. So this is H by invariant. Okay. Well, why is it H by invariance? As a function on G, right? So if I put an H here, well, that H is here, but that does not do anything to E1. If I put an H on the left side, that's here, so it's a representation, so it splits, it's a unitary representation, so this guy goes to the other side as H inverse, but H inverse will also fix E1. Okay, so this is H by invariant. And you look at the other elements in the column, so I have row dk1, remember it's a dk cross dk matrix. 1 tells me it's in the first column, G, so this is okay, G E1k E dk, right? Yeah. Well, this function is not H by invariant because this is not fixed by the representation, but E1 is fixed, so it's still right H invariant, right? I put a H here, nothing happens. Okay, if I put an H here, it will go there and something will happen. Okay, so whatever is remaining is right H invariant. Okay, so these are all functions on G by H, right? Because they are all right H invariant. So for each representation, you look at the first column. Okay, that gives you right H invariant function. You put together all of them, you will get L2 of G by H. Okay, or the space. So L2 of L2 of G by H, well, which is identified with L2 of X and so on, is the span of these guys, the first column of each representation. So I have row 1 k G, okay, up to row dk 1 G. So that gives me just the space Vk, and then you add on k, right? So k equal to 0 to infinity. So you look at the finite linear combination of these matrix entries and take the closure. Okay, so that will be your L2 of G by H, right? All the right H invariant functions will be captured by these guys. So every now and then I will write row of ij at x, where x is in capital X, but that is allowed because these are all functions on G by H, right? So I will go back and forth between x and G. It should not cause any confusion. And so any element has any function in L2 of X has a Fourier expansion, right? Using these matrix entries. That is the spherical harmonic expansion. The Fourier expansion. I can write f of x to be summation. Okay, so here I equal to 1 to dk. So this is just writing this in words, right? Okay, Ci1k. So those are the coefficients, and you have the matrix entries. X. Well, what are the coefficients? These are simply inner product of f with, so maybe f of y, rho I1 k y whole bar d mu y, right? So this is the G invariant measure on X, right? So that is simply writing this in words. Right. So you can expand any L2 function in terms of those matrix entries. Okay, so to each of this, to each space Vk, we associate function. Okay, so this is the zonal spherical harmonic, zonal spherical function. Zonal spherical function, which we denote by JK. So this is whatever is in the book of Conway and AKXY. Well, what is this? So this is given by these matrix entries. So dk, forget about the constant because there is always a normalizing factor in the orthonormal basis part. Okay, so and one has to multiply by the root of the dimension, right, to get a orthonormal basis. So that's where the dk comes from. But what is important is what follows. So you sum up these things. So R rho I1 k, let me write down and then explain. X rho I1 k y bar. So that's our zonal spherical function. I'll come to the well, we'll see what it is in the case of the sphere. So what am I doing here? So this is simply the first column of the representation, right? And you are simply multiplying by taking a complex conjugate evaluated at a point y. So this is like a gram matrix. Okay, so that is why it becomes positive definite soon. So yeah. Well, okay. So here maybe I should put a dk or 1 by dk or something. So some constant. Okay. So let's. Yeah. Thank you. Okay. Yeah, that will do. So yeah, most probably it's root dk or dk. Okay. So this is the zonal. So these are called spherical functions. So they well, the way it's written is slightly different from what you will see in the literature, because we want to write it as a G invariant kernel. So you will see that in the case of sphere, you actually get, because it's going to be G invariant, it will be a function on -1, 1. So you can think of it as a H bi-invariant function on G, and it would be the usual spherical function. So they are sort of matrix entries of 1/1 matrix entries of class 1 representations. Okay, so that. So let's write down the properties of this maybe here. Okay. Properties of JK. So you would have noticed that I have switched to x and y, where x and y are in capital. Okay. So I'm viewing them as functions on capital X now, which is G by H. Okay, so first property is that it is a positive definite kernel. PD kernel on X cross. All these are true in general. Okay, we have not restricted ourselves to sphere yet. Okay, only at the last few steps I'll do that. So this is a positive definite kernel. I'll tell you why. This is independent of the basis, whatever basis you choose. Well, of course, the first one has to be H fixed. Okay, so you can change any other one, so it doesn't really matter in the. And G, this is G invariant. So G invariant kernel. So JK of Gx Gy is JK of X comma Y, right, for every G in G. Well, there is one more which I will write down. Yeah, sorry.
Which basis you mean E?
Yeah, so JK is written as product of matrix entries, and the matrix entries are obtained by a basis. By this basis, yeah. Okay, yeah. So, yeah. So all of this follows immediately. So let us, maybe I'll use this space too. Okay. So those three properties follows from simply writing down the expression for jk in a slightly neater manner. Okay, that's a product and so on. So that's simply the inner product of so rho k, so kth representation g acting on the first vector, okay, and you take rho. Okay, too many identifications. So kh e1. So both are e1. The first h fixed vector, but g and h are, so g and h are from capital G. Here you have x and y, there you have g and h. So g should be the point corresponding to x, right? So g dot x naught should be x, and h dot x naught should be y. Okay. So I've sort of gone to the group to write down the function. Well, that is, which also can be written as, you can bring this here because it's a unitary representation, so you will get Rk of H inverse G, which you should be reminded of what I said in the beginning, even K. Okay, so many things follow from this immediately. Well, they are equal because this is the first column, and right, and you are taking the inner product, so you will get the expression. So that is a trivial thing. Even is H fixed, so whatever element of H here doesn't matter. So it's actually a function on G by H, right? In fact, it is, if you bring this here, you can think of this as a function defined on G, and you will see that it is H by invariant. Okay. Yeah, I can write that as well. So if psi of G equal to rho k G E1 k E1 k, because both are E1, right? E, the first vector, so it's fixed by H. So this is a H by invariant function, okay, on G. So that is the 1/1 entry of a class 1 representation, and that is your spherical function. Okay. So if you expand this and then take the inner product, you will get exactly this. Okay, so the proof of that is very trivial, but everything else follows from that, right? Because this, once you write this, the only E1, the first vector matters. So it is independent of the basis as long as the first vector is fixed by H. It's G invariant. Okay, why is it G invariant? Yeah, so if I put anything here, so let's put a G1 here, G1 and G1 here. So that will get cancelled, right? Because I'll have a G1 inverse and G1. So that will get cancelled. I mean, any function of this kind is G invariant. That's what I said in the beginning, right? If you look at a function on G cross G, and if you do this, then you get a G invariant kernel. So all these properties are, well, it's positive definitely, that's the important one, which I didn't. But that is because it's the matrix entry, it's a diagonal matrix entry of a unitary representation. So here is that remark. So I have some group G, and let's say pi is a unitary representation of G, then the function phi of x equal to pi x, some vector you take, let's say w. Okay, so w is a vector in the representation space, in the Hilbert space, right? Representation space is positive definite. So that's a easy proof. So remember, you are on the group. So if I look at phi of xj inverse xi, right? That is the matrix you will be looking at, and then you multiply by ai aj bar, right? So you want to know what happens to this. Okay, so what is that? Because you can write down phi of xj inverse xi, so you will have xi here and xj will come here. Okay, so then you sum up as you do with exponentials, you will simply get that this is pi of xj w no, what do I want to say? No, I want the AIs also, right? So AJ, right? And then you take the norm square. Okay, so that's, and it's like a gram matrix again. So you have to get that. So any diagonal matrix entry of a unitary representation is positive definite on G. So in particular, JK is positive definite. So all that now we want to say is to put together these things and say that any G invariant positive definite kernel on X is a sum of these guys. Okay, so that is sort of easy to see now. If you think of H bi-invariant functions on G, they will have to be spanned by those spherical functions. Okay, so that is the representation theoretic interpretation if you want. Okay. Let's see. I have enough. Okay, so I'll also say that the Zonal spherical function we have written down for the sphere, it is the Jacobi polynomials or Legendre polynomials which was defined earlier, right? So let me perhaps make that connection also. So that property 4, if you like. So when x is Sn minus 1, jk of x comma y is, so there was a constant, so well pk, let me, okay, so pk alpha beta of x dot y, okay, divided by some constant, so that is, well, k plus alpha k, okay. What is alpha? Alpha and beta are n minus 3 by 2. Okay. So remember, these were the Jacobi polynomials which was defined earlier, Jacobi polynomials with parameters alpha and beta. Okay. So you divide it by 1 so that it is 1 at the identity. Okay. That, I mean, divide by this constant so that it's 1 at the identity. Okay, so maybe I can explain why this is true. So, okay, proof for this, so that we have the complete connection now. You can probably look at the Laplacian and say that they are same, but well, they are orthogonal. So if I change k, if I look at k and L, where k is not equal to L, because they come from different representation spaces, they are orthogonal to each other. But since it's a function of x dot y, because it's G invariant, it's a function of x dot y, the integral over Sn minus 1 reduces to an integral over minus 1 to 1, which gives you orthogonal polynomials there, which are Jacobi polynomials. Okay, so that's the proof. So let's write jk of x comma y. Remember, it's G invariant, so it's a function of x dot y. So let's write this as phi k of x dot y. Right? It's a function on minus 1 1. Okay. So by Schur's lemma, they are orthogonal to each other. So I can write this as n minus 1 jk of x comma y jl x comma y, okay, d mu y equal to 0. Okay, so for any x, right? Because where is our jk? Yeah. So this, if I fix one variable, it is a linear combination of certain matrix entries. And so if k and l are different, they come from orthogonal pieces. So they are orthogonal to each other. Maybe I should also say that in the case of the sphere, I can make this real valued by taking, because you're looking at polynomials, right? So you can choose, for orthonormal basis, you can choose real valued polynomials, and you will get that is actually a real valued function. Okay, so I won't put the bar here. So because this is G invariant, etc., this integral reduces to so Sn instead of Sn minus 1, you will have some constant times integral minus 1 to 1, and phi k x dot y, right? So I'll have phi k of t, phi l of t, and then the projection of the measure and so on. So 1 minus t square to the n minus 3 by 2 dt equals 0, right? Because of the orthogonality. But these are polynomials in T, right? So because of that, and the uniqueness of the orthogonal polynomials in that space, we'll get that this has to be equal to. So this implies that phi k will have to be equal to pk alpha beta, and maybe some constants. Okay, so I will not bother about the constants. Okay, so the Schur's orthogonality implies orthogonality in -1, 1, and by uniqueness of orthogonal polynomials, we have the Zonal spherical functions to be given by Jacobi polynomials with these parameters, which are precisely the Gegenberg ones, which was defined in the last class. Okay, so that I think we are. Okay, so we can write down the theorem and then tell you why it is true and then stop. Okay, so theorem. So theorem in general it's due to Bochner. On the sphere it's due to Schoenberg. Okay. So I have x to be equal to g by h, that is our space. Then a kernel from x cross x to, well, complex value, continuous, so I'll assume it's continuous, is positive definite kernel, which is G invariant. So that is the important part, which is G invariant. If and only if k is given by those Zonal spherical functions, okay, k equal to 0 to infinity, where combination is a positive linear combination and it's summable, the coefficients are summable. Okay, so that's the theorem. Oh, okay, didn't use the space. So every G invariant positive definite kernel on X is given by a infinite positive linear combination of zonal spherical functions. Okay, so certain things are easy. First of all, each jk is a positive definite kernel, we know that. And so if you sum up, take positive linear combinations, even infinite ones, you will still get a positive definite kernel. Okay, so you have to show that it converges, but jk is bounded by 1. Well, why? Because it's given by a matrix entry of a unitary representation, right? So it's bounded by 1. So if AK converges, then this will converge, and so it will be a positive definite kernel. So, and it's G invariant. So one way is trivial, right? So this portion is trivial. Okay, the important part is that if I have a positive definite kernel which is G invariant, it is given by a combination like this. Okay, so so here I'll restrict myself to the sphere case. Okay, one can do this in general. In fact, it's under some conditions it will be much easier to say this in the general case, because these are given by h bi-invariant functions on G, and so any h bi-invariant positive definite kernel is sort of sum of such things. Okay, so I mean it's like span of spherical functions will give you all h bi-invariant functions on G. Okay, so that's a general nonsense, right? Like all metric entries will give you all L2 functions. Among them, if you have invariance, you look at the corresponding metric entries with the same invariance property. Okay, so that is all it is. Okay, so in this case, so we are we'll assume X is the sphere. Okay, now I'll so the kernel kxy is G invariant. Okay, so it's SON invariant. So it's a function of x dot y, right? So we'll write this as well. Now I'm going to use Schoenberg's notation. So I'll write it as f of cos theta. So write k of x comma y is f of cos theta. So x dot y is cos theta. So f is a function. Well, it's SON invariant, so I can change x and y, right? So x you write in polar coordinates, cos theta, etc., and y you can simply take the vector 1 0 0 0, right? You can, because it's SON invariant, I can map this guy to any vector I want on the sphere. So now I have to tell you 2-3 things, and then proof is over. So this is a continuous function. Well, I started with a nice k. So it will be in L2 with respect to the measure associated with the Jacobi polynomials. And so it has an expansion in terms of Jacobi polynomials, right? Because that's an orthogonal basis for L2. Okay, so, well, okay, so let me write one more step so that it's clear. So if I look at f of x dot E1, so this would be in L2 of, well, what is E1? Okay, so now I have, forget about all the matrix entries. So E1 is this vector. Okay, so first basis vector. So this will be in L2, and so it can be expanded, right? So f of, well, it's in L2, which will tell me that when I write down the L2 norm of f, because the function is of this form, it reduces to an integral over minus 1 1, right? Which gives me that measure. So f of cos theta will be in that space. Okay, so f of cos theta will belong to L2 of minus 1 1 with respect to whatever measure you want, right? Whatever is projected from here. And so it can be expanded in terms of an orthogonal basis, which is our Jacobi polynomials. So can be expanded. So that's an L2 expansion, expanded in terms of pk alpha beta, okay, where alpha and beta are n minus 3 by 2. Right, that corresponds to the power you get there when you project the measure to minus 1 1. The parameters correspond to the power of the measure there. So write f of cos theta as, so write f of cos theta as summation ak pk alpha beta cos theta, where, so alpha and beta, so I keep writing this n minus 3 by 2, so, okay. So what is AK? AK is the coefficient of f in the expansion, right? So you will get AK by taking the inner product of f with the corresponding orthonormal vector. Okay, so AK is 0 to pi f of cos theta. Okay, 0 to pi, I should have said 0 to pi there also. So this is actually 0 to pi. And the range of cos theta is minus 1 1, but when you write it this form, this is 0 to pi. Okay. Anyway, those things don't. Cos theta, so sin theta to the n minus 2 or n minus 3. Some power will come. Okay. Again, don't need to bother too much about it. What we want to say is this guy is a positive real number. So for that we change this into, we have done this several times now. From sphere we always come down to either 0 pi or minus 1 1, we go the other way. So this is simply some constant in Sn minus 1 f of x dot e1. E1 is the vector there. That is what gives me cos theta. Pk so n minus 3 by 2, n minus 3 by 2. So that is the parameters x dot e1 d mu x. Okay. So I mean this is all simply change of variable, right? There is nothing else. This guy is positive. Okay. So why is that? Well, that's a property of positive definite kernels, which I should have told you earlier. So f is positive definite. Pk is positive definite, right? Because this is given by, this is our jk, right? The zonal spherical function. So this is positive definite, this is positive definite. So product is positive definite. And this follows from the integral condition we have. Okay, so if I look at kxy, so where k is a PD kernel, any positive definite kernel, then remember positive definite meant we had phi of x, phi of y bar, d mu x, d mu y, right? That has to be positive for all continuous functions. You take phi to be 1, so that is what was mentioned in last lecture of Abhinav, right? So you take all the vectors to be 1, then the sum of the entries is positive. Here instead of I'm using the continuous version of that, which is the integral. So if you take those functions to be 1, so this is simply d mu x, d mu y. And of course, this is independent of one of the variables, right? So only one integral will survive. So this is actually equal to integral over Sn minus 1. K of I can write it as x1 e1, right? I can change this to any vector I want, and then I'll have x dot e1 or x e1 d mu x. So other variable is forgotten. So which means the integral of k is positive for any positive definite kernel, right? So this the product is a positive definite kernel, so its integral is positive. So AK is a positive. So I started with a G invariant positive definite kernel. Writing it in this form, I expanded it in terms of Jacobi polynomials, and I'm saying the coefficients are positive, right? So that is part of the theorem. So I want to say that the sum is finite. Well, it's not the sum. We have to normalize this, so I'll not bother about that. Because this is not exactly the zonal spherical function, because zonal spherical function will take 1 at identity. So this guy has to be 1. It has to be divided by k plus alpha choose k or whatever that constant is. Okay, so all that we will show is this converges absolutely. That will do. Okay, for that we need. Okay, so I can use this part. Another result from analysis, which most of you know. This is the Abel summability of the expansion, spherical harmonic expansion. So, okay, so let's go back to the circle. If I have a function on the circle, I can extend it as a harmonic function inside, right? So circle has a Fourier series expansion, and each e to the I n theta extends as a harmonic function. And the harmonic function, if you take the radial limits, you will get the boundary value again. Okay, so that is the Abel summability for the Fourier series. That is true in general for spheres. So if I have a continuous function on the sphere, the spherical harmonic, so each piece is actually a harmonic polynomial. So that extends as a harmonic function inside. And the radial limit will give me the boundary value. That's again the Abel summability for that expansion. So we'll use that. So apply. At theta equals 0 for the expansion there. So you look at the finite sum to start with, k equal to 0 to L AK modulus of PK alpha beta cos theta. So I'm taking the finite sum and trying to prove it converges absolutely. So this is less than or equal to, okay, here is another one where another property which I should have told you earlier, PK alpha 1 is cos theta equal to 0. So that's a property of positive definite kernels again. If I have a, so kxy is bounded by kx, like Schwarz inequality, right? Cauchy-Schwarz inequality. Kxy is like an inner product. So it is bounded by kxx times kyy to the half. Okay, so I should leave it as an exercise, easy exercise. So modulus of, whenever you have a positive definite kernel, kxy is less than or equal to, kxx is positive always. That's like the diagonal entry of the positive definite matrices, right? So that is yy to the half, okay? So we use that, so it's like, well, if you have a positive definite function on a group, then the value at the identity is the maximum, okay? So that's what essentially we are using. So you use that, you will get this. But there is able summability at 1, so this is equal to limit r going to 1, summation k equal to 0 to infinity, r to the k pk alpha 1. But this, I know it converges to f of 1, right? F cos theta at 0. So that is finite, which means that this is absolutely summable. So you get your theorem. I think, yeah, that's all I want to say. Yeah, well, it doesn't explicitly say rank 1 compact, it's compact symmetric spaces, but the conditions essentially will imply that. So yeah, okay, let me write down the references for. So apart from the book which Abhinav has already written down, you can look at the papers by Schoenberg and Bochner. So that is so this is positive definite functions on spheres. Okay, so this came in Duke J Math 1942. Okay, so Bochner, so this is titled Hilbert distances and positive definite functions. Okay, so this is analysis of math 1941, so 42. That's interesting because Bochner's result is more general. It appeared in 1941, but Schoenberg already had the result in 1940. Okay, it appeared only in 42. I'll give you one more reference where the abstract stuff versus the concrete stuff, where the connections are all made, where I sort of said Laplacian saves the day and so on. So for all that, you can refer to Kaufman and Weiss. So Ronald Kaufman, so R Kaufman and Guido Weiss. So this is an expository article, representations of compact groups and spherical harmonics. Okay, so ensign math. This is free. Special functions and representations will tell you almost everything you want to know. Okay. So